this section, we'll investigate the next important component of electrical transport, which is diffusive transport. So the essential idea behind diffusive transport is that if you have a large concentration of holes or electrons, they tend to repel each other and push themselves apart. They're also, remember, moving with their random thermal velocities throughout the crystal in random patterns called Brownian motion. And so they're moving with this V thermal. And on average, if you try to ask the question, how far away from the starting point do they get in a certain amount of time, you find out that the result is square root of d times delta t, whatever delta t you're asking the question for. And this circle that I've drawn is really the circle with the radius given by the sigma of a Gaussian distribution or a normal distribution representing the random, the histogram of random positions that the electron has occupied at different times. So this sigma is actually the average value of x squared, and that's where this comes from. So what's the consequence of this spreading out of electrons as a function of time? Well, it means that a current will actually flow if electrons are introduced or holes are introduced in one region but not in others. So one way that we can represent this is to consider a region where the n is a function of x. So the number density of electrons per cubic centimeter is changing versus distance. So we'll ask the question about what are the particle fluxes coming to this certain position x naught. So if we have the region just to the right of x naught, on average, half of its electrons in this region here are traveling to the right and half to the left. So the particle flux there will be n of x plus L times 1/2 times the thermal velocity. Now, the same could be said for the other side. We'll have half of the electrons moving there, half there. And again, the part that will end up at this point, x naught, is this one. So we'll have 1/2 n of x minus L times V thermal equal to the flux going this way and the flux going that way. So by considering these fluxes, we can then compute the total flux, and this is going to be the difference between these two. And it ends up that the total flux will be some diffusion coefficient times the derivative of n of x at the point x naught. So the derivative of the carrier distribution is providing the driving force for this particle flux. And we can then relate the particle flux to the current by introducing the electron charge, the charge per electron. And when you look at the origin of this diffusion coefficient, it's going to be the thermal velocity times some distance L, which is somewhere on the order of interatomic spacings up to the mean free path. So now we can add our two components of current together to get the total current. We can also differentiate between electrons and holes. So the holes have an analogous equation, and our overall grand total is the sum of all four of these components. Now, while we're on the subject of the diffusion coefficient, let's introduce one important relation named after Albert Einstein. And the key thought here is that the random motion that we described as driving diffusion, that Brownian motion, is actually connected to the scattering events and the random motion of the electrons during drift also. So the Einstein relation states, and say it out loud because it rhymes, d over mu is kBt over q. If you remember that rhyme, you'll never forget it. So the fact that these are related actually means that the origins of the electrical resistivity and the impediments to diffusion, meaning the how slow the electrons diffuse out through the material, are both originating from the same physical process, as I motivated before, that's scattering events and random thermal excitation of the electrons, making them go in all sorts of different random ways. So in this short section, we've investigated the diffusive conductivity, or the diffusive transport. And we've also introduced an important relation that connects the two types of transport, the drift transport through mu and the diffusive transport through the diffusion coefficient.